Okay, so so yesterday we finished by stating a part of lemma 3.7. So as I said, this lemma is purely algebraic. It's not about category. We are just considering a K-algebra, a finite set O, and a finite set for any element in O. And we are considering a family, a set of non-zero elements in A indexed as follows, for 1x in big O and Ij in Ix, such examples. And we assume that this element satisfy this relation, where this is a Kronecker delta, this is a constant, non-zero constant, and you have here another element of this family. So what about this? So as I said orally last time, yesterday, but I didn't write. This family, this relation forces the family to be linearly independent. So yeah, this red line is just for mentioning that it's a frontier between the previous course and the next course. So it has nothing to do with the statement of the lemma. Okay, so then the elements are linearly independent. Element tau xij x in O, ij in Ix are linearly independent. And so generate a K-algebra, K-subalgebra, isomorphic to the direct sum mnx of K if x in the set with nx to be the cardinal of this set. So we are assume finite set. Yeah, the cardinal of the set. So in fact, I will prove in details this part, linearly independent, and the fact that it generates this K subalgebra is immediate from this relation, because in fact this are the relation of elementary matrix. You consider you have elementary matrix which are equal to 1 in some entry and 0 everywhere. You get such a relation. So in fact, of course, it is indexed here by x. But if you forget about x, if you fix x, then you have the relation of elementary matrix. And so they generate the full matrix. Yeah. I don't know whether there is another argument for that. Let me check. Anyway, if you can prove it that generate a simple algebra of cardinal D square, then it will be matrix algebra also. But why it should be simple? Anyway, this is just a relation of elementary matrix. Okay, so proof. Suppose that. So we want to prove that linearly independent. So the usual way to do that is to suppose there is a linear sum of all these elements which equal to 0, and we show that every multiplicative constant of this linear sum is equal to 0. So suppose that 0 equal sum of x in tau I j in ix lambda x. So you have the coefficient x I j. So you have that. Suppose you have that, and we want to prove that each coefficient is equal to 0. So we will use the relation. Observe that following. So you will, in fact, we will, the idea is just to consider this, and we will multiply by something specific on the left and the right, something relevant, in order to vanish everything except one entry of the sum. And so that will isolate one multiplicative constant, which will be automatically equal to 0. So we will multiply, in fact, by tau x prime kl on the left and tau x prime k, yeah, the same on the right. And so we want to, let me show you what we get first for this x I j. What do you get here? So by, you just use a relation here 2 times, and you automatically get that it is equal to dx square Kronecker delta x x prime Kronecker delta li Kronecker delta gk tau of x kl. Yeah. So we get 0 equal tau x prime kl times the sum x in O ij in ix of lambda x ij tau x ij tau x prime kl, which is equal to okay, so I'm going too slowly here. Sum of x ij lambda x ij tau x prime l tau x ij tau x prime kl no prime. So I'm sorry, it's too slow, too much detail for something so obvious. Anyway, it will be Quick, so this is equal to. So you replace this like this. Then here you have a sum, you have 3 parameters, but you have 3 Kronecker delta. So that fix everything. You have no choice but to get it equal to dx squared lambda xkl tau of x. So prime, tau x prime kl. Okay. So this is equal to 0. Then thus the constant should be 0 because dx is non-zero, and that is not that and that are non-zero. So this is a constant which should be 0 for all x prime into kl in ix prime here. Okay, so you have what we wanted to prove, that you assume a linear dependence and you get that the coefficients are all 0. So it should be linearly independent. And for the rest of the statement, as I said, okay. Should I write something for the last part? For the last part of the statement, just consider how a matrix algebra is generated by elementary matrices EIJ anyway. So you should know what is elementary matrix. So the last part of the statement, just consider how a matrix algebra is generated by elementary matrices. So I mean, yeah, it's okay. So I mean, the matrix algebra is completely determined by generator and relation. The generator has the matrix algebra, and the relation are this kind of relation. Okay. So, okay. What about? Okay. Now we will state and prove one key proposition of the course called the resolution of identity. And in fact, we will prove something a bit more general than just for the identity. In fact, we will prove something, the resolution of any morphism between two objects, between one object and itself. But the application, what we will really need is when the object, when the morphism is the identity. So let me, yeah. So for that, we will first, before stating that, I need to recall something from EGNO book. Recall from EGNO book. A proposition 484 that if you have a simple object in a pivotal fusion category, then the dimension is non-zero. So that for all. So we proved that, in fact, in previous semesters. So you can refer to previous semester also if you prefer. In a pivotal category, so for all simple object X in a pivotal fusion category, then its dimension, according to the pivotal structure, is non-zero. Okay. So proposition, resolution of identity. Identity. Remember that in the introduction part, I mentioned the resolution of identity to replace three string by a sum of something like that. In fact, when we consider the Dylan-Thurston diagram picture for the triangular prism equation, I said that somewhere you should consider the resolution of identity. We need to replace, in fact, so I will redraw this picture at the end of the statement of the proposition where the precise statement will be written. This proposition has no picture. So it will be written algebraically, but I will draw this picture in front of the algebraic relation for the identity. So the proposition will be quite long to state and quite long to prove. So it's more or less the first non-trivial, non-straightforward result, at least in the sense of the length of the proof. So let's see, be a pivotal fusion category. With pivotal structure A. In fact, so this the result I will state here. So it is stated and proved in the paper, in my paper I mentioned. I don't know if it is proved before in the literature, in fact, but at least it should be considered as more or less as a folklore result, because it's for people who use this, who are working with the tensor category and graphical calculus, you may use such result. I don't know if it is proved in full details and in full generality as in this proposition. Okay, so let's see be a pivotal fusion category with pivotal structure A. What I can say, at least, I did not see this result in the EGNO book. So fix an object T in the category and let X be a simple object. So another object in C also. Let OT be the set of simple object, simple subobject of T. And here you recognize the notation O. So this, we are in a fusion category, so this set is finite. And in fact, this notation, O, big O corresponds big O we mentioned in the previous result, previous lemma. So we will apply the previous lemma with such involving this set. Okay, so the finite set of all the simple objects, subobject of T, up to isomorphism, of course. Otherwise, it will not be finite a priori. So, okay. So now we state the existence of bases, of two bases. There exist basis BXI I in some index set IX of home CTX, and you recognize also the set IX here. Even if, yeah, okay. And B X I prime I in IX of basis of home CXT. Let me check time. So it remains 10 minutes before the, no, 20 minutes. 20 minutes before the pause. Okay, so you state the existence of two bases such that two bases of this two-home space such that trace of B prime xi composed with bx equals a trace of x composed with b I equal delta I. Okay. So now we will consider this as element of home space from T to itself, or from X to itself. Yeah, one of the two. And we will state that there are bases, but at least, yeah, we will just consider this one. Okay. So let tau xij. Now you recognize also this notation from the previous lemma again. To be b prime x xi composed with b x j. So its trace is Kronecker delta by the previous line. Then tau x, then you will get the expecting relation from the previous lemma. KL equal delta XX prime, delta Kronecker delta JK, dimension of X inverse. That's why we recall that the dimension is non-zero. Otherwise, this does not work. And tau XIL. Okay, so this is the relation we will prove. And what about next? So then you have that, and the set tau xij, so x in O of t, ij in I of x, is a basis of home C of T2. So by the previous lemma, we will say that it is already linearly independent. So we will just need to prove that the cardinal equals the dimension. And so as I said, the statement is long. And for all gamma in this home space, it's a basis. So there is a decomposition. And the coefficient of the decomposition are as follows. The sum for x in O of t, the sum for ij in ix, dimension x, trace of gamma xij, tau of xij. This is the general statement. And to get the resolution of identity, we apply that to x. To gamma equals the identity. So if you apply gamma, if you consider gamma equal identity, you get the first you get the following particular case. In particular, so resolution of identity. If gamma is the identity of T, gamma equals the identity of T, then identity of T equal, and the previous formula can be simplified in this case. Sum for x in O of t, sum only for I in Ix, only one coefficient, dimension x tau of xij. Okay, so that will be used. And okay, and then what? So here it's a good moment to draw the picture I mentioned. So, let me check something. identity. Yeah, here it's I. And so wait. So fix an object T. Okay. Let X be a simple object. So here there may be a confusion. I'm confused with something. Let me rewrite. So the problem here, we consider X. So you fix X here. So what? So okay, let me reread. So you fix T, and X is simple. You consider this set, okay, of simple subobject, so that's okay. And we consider, so there exists basis for that and that. So here, X is fixed, okay, such that that is equal to that. Okay, here X is fixed. Then you have that X is fixed. Okay. So then X is no more fixed. Now X vary in. So for the first time here, X vary in the set of simple subobject of T. So we did not use this set before. Okay. Okay. So it's a basis of that. So for all we have that. So that's okay. So if you apply to the identity, so here the identity will be, you get only that. So this trace will be a Kronecker delta for ij. And so you can take I equal j. Okay. So my problem here is if I want to draw, so you have the T. So if my example was if I take T to be 3, T equal to x1 tensor x2 tensor x3. Now you consider T x1, x2, x3. So the identity of T, that should be equal to a sum of something like that, which is tau. Where is tau? Xii. So anyway, maybe I cannot spend too much time on that. This will be applied later, but for here there is no problem. So this is where Bx, so start from T and finish here. So your composition, you go through X like that. So if you want to draw the picture here, it as follow. So picture. Take t equal x1 tensor x2 tensor x3. Then the identity of t equal like that, x1, x2, x3 is equal to a sum. So let me just write over something. I don't just want to draw the picture with some coefficient of some morphism. You have something here, another morphism like that. So here you have x1, x2, x3, x1, x2, x3, and here you have sum over. So you have this sum. So if I write, so there are some x involving in this sum. So you can write some x here. Okay. So sum for x. Sum for x. Sum for something with some coefficient. Okay. So when for the component x equal 1, so assume that you have a component x equal 1, then 1 is written without, you don't draw it. So this component, you get something like that. But something like that, which correspond to what we drew before, something like that. So something like that. And here, this is the pictorial representation we saw in the introduction. This pictorial representation represents this morphism. So you have this. We will see that we will have to write, in fact, the name of the morphism somewhere in one of the three angles. But for in fact, when we will use this result, we will not need all the components different from 1 here will be cancelled for a reason I forgot. So you will only get that this, yeah, it will be cancelled because of sure lemma, something like that. Because here it's simple, and we have a big graph with something else here, and you apply sure lemma, you will have some 1 here, etc. Anyway, so you finish by the fact that you can replace that by something like that. In the application we will mention later, we will apply the resolution of identity to replace that by that, where all the components different from 1 here will be cancelled, because all the components will be cancelled anyway. So we only need to care about the component equal 1, and you get something like that, because here you are. Okay. So this picture was not pictorial ID, I should say. It's not a pictorial proof or pictorial. It is not pictorial ID. It's not pictorial graphical calculus as we do proof before. It's just to what we mean in the introduction. And later in the course, we will see more details about that. So just to illustrate, just to motivate this result. Okay. Okay. So, now pictorial ID. I don't like that because it looks like it will be the ID of the proof, which is not. What should I write? I just no picture. Anyway. Okay, proof. Or maybe we can make the pause now. 2 minutes in advance. We will restart 2 minutes. Yeah, I will do that. So pause. 6, 3, 2, 8. Okay, so the rest of today's session will be dedicated to prove this proposition. I hope we will have time to finish. I see how many pages on 1, 2, 3 pages. Okay, proof. Okay, so about the basis mentioned here, the exist basis. This basis exists by using lemma 3.6 with y equal to the right dual of t. So let me go back to 3.6 here. Okay. We will use that. So you have, okay, okay. So it's here. You have this basis. And we need to use y equal, you need to write here y equal the right dual of t. And then you will get y, then y star will be t, and xt, tx. And the rest should be okay, following 3.5. Pivotal fusion category, pivotal structure. Oh, this one is very bad. Excellent. To object the extension. So using this lemma, you automatically get the expected basis. So the basis mentioned at the beginning exists by lemma 3.6 with y equals the right dual of t. Okay, and you have, so this lemma 3.6 also you have the relation. You have the, you have that also, no? I guess, what do you have also? 3.6. You have that, and you have also the relation with the trace. Okay. You have the trace. You have that. You have the basis. So we have that automatically also. Okay. So. So what about the notation? So I have this basis. Here the notation is different from 3.6. It's B, written with some B. And we will consider tau. So we'll consider the composition of two, something like that. So up to now we have that. We have that. Now we will consider that. Okay. So, and a composition of two such. So tau xij compose tau x prime kl equal, by definition, xj composed with b prime x prime k composed with b x prime l. So by associativity. Change color. Nice. So associativity. You can move the parenthesis. So it's just the associativity of the algebra. So b x I prime compose bx j compose b prime x prime k compose b x prime l. Okay. And now we consider this other composition, which is between x and x. So it's the Hom space is one-dimensional by Schur lemma. And the fact pivotal fusion category. So you have, I mentioned that here, the field here should always be algebraically closed to get that Schur lemma provide one-dimensionality for Hom space between a simple object and itself. In general, the Hom space, the Schur lemma is saying that the Hom space between a simple object and itself is a division algebra. And you need to say that a division algebra, a finite-dimensional division algebra over a field which is algebraically closed is trivial. It's just the field. But it's not true if the field is not algebraically closed. So everywhere you need the field to be algebraically closed. So let me write it here, but it should be written from the beginning. Recall that the field is always assumed algebraically closed. Otherwise, you may have problem with Schur lemma. Otherwise, the dimension of so the home space between a simple object and itself will be a division algebra, which will not necessarily be trivial. So we cannot say it to be one dimension. Okay. So associativity. So now, but bxj compose b prime x prime k is a morphism between x and itself, and x is assumed to be x prime and x, but both are assumed to be simple. So by Schur lemma, this is zero-dimensional if x is different from x prime, and one-dimensional if it is equal. Remember that x and x prime I consider up to isomorphism. So if they are different, they are not isomorphic. Delta Kronecker delta x prime dimensional by Schur's lemma. So by lemma 2.9. So let me briefly recall what this lemma states. I will not come back because it may be too far. So this lemma is stating something that alpha, you can rewrite alpha in a such one-dimensional home space like that. Trace of alpha, identity of x. So if you have an alpha between if you have a morphism alpha between x and itself, then it can be written like that. Okay. Then by this lemma, bx, which is of the form of alpha. So bxj compose b prime x prime k is our alpha, is delta. So what? So delta x prime by Schur lemma, dimension x prime inverse, dimension x inverse, trace of alpha, so trace of bxj composed with b prime x k. So now x equal x prime. So identity of x, okay, which is equal to delta x prime dimension x inverse, and so we know that this is a Kronecker delta ijk by lemma 3.6. So it is delta jk identity of x. Okay. Okay, so we consider this one. We can replace this one by that, and you have a Kronecker delta. So then you can simplify this formula. So then this equal to something like that simplified. So then thus tau xij compose tau x prime kl equal b prime xi composed with that which is above x prime dimension x inverse delta jk identity of x composed bx prime l. So it is equal to So you move everything, every Kronecker delta on the left, delta J, K, dimension X inverse. You can delete, you can remove the identity, and you just get Bxi prime compose Bx prime L. And yeah, you can take X prime equal X, so you don't need to put a prime here. Okay. And it is equal to, and this is nothing but the definition of tau xil. Here. So you get that this is nothing but Kronecker delta x prime delta J K dimension X inverse tau xil, just by definition. By definition. Okay. So okay. So we get maybe a bit more. So we get that. So we prove that. So now we will use our previous lemma to say that this is a relation from our previous lemma implying that they are linearly independent. But before we need to show that they are non-zero. So tau xij is non-zero because tau xij composed with tau xji equal dimension X inverse tau xii and trace of tau xii equal 1. So you have this is of trace 1, so it is non-zero, so each component is non-zero. So this is non-zero. Okay. So now we apply the lemma we proved at the beginning of today's session. So by lemma 3.7, the element of the set tau x, let me write it. Yeah. Tau xij x in P of t ij in ix. So this element are linearly independent. Linearly independent. In fact, we just need linearly independent. We don't need here the method that generates this matrix algebra. I don't know if we need this matrix algebra later. If I just stated just for the beauty of mathematics. Okay. So I am linearly independent. Now we need to talk about the. So we need that we want them to be a basis of the Hom space between T and itself. So we want this to have this. We want the cardinal of this set to be equal to the dimension of this Hom space. So let me consider this dimension, but observe that dimension home C T equal. So I will provide the details of that in the paper. There is no details, but it may be useful to provide the details here. So it's an easy exercise. This first equality is an easy exercise I will explain. And this is equal to the sum of x in OT cardinal of x squared by, here is just my definition of IX. IX is just the index for the basis, for this basis. So of course, this dimension is equal to the cardinal of it. So now, what about this one? So it's an easy exercise. T is isomorphic to a sum of so you have a multiplicity space tensor X. So you have you consider the simple component of T up to isomorphism, but you can have several occurrences. You can have several components which are isomorphic. So you need to put a multiplicity space. Okay. Multiplicity space. Multiplicity space. So remember that this tensor product is not, this is not an object of the category. This just means we are considering dimension of that times this object. Okay. So be careful, this is not the tensor product of the tensor category. Just a notation. So home C T is isomorphic to the direct sum of x prime in OT we just developed of mx tensor mx prime tensor home C x prime. So the dimension of that is given by a sum over x prime in OT of the dimension of each component mx dimension k mx prime and by Schur-Lemma Kronecker delta, because x and x prime are simple, which is equal to you can take x equal x prime, so sum for x in the simple component of T up to isomorphism dimension k of mx squared. So you see the square. And it is equal to dimension x of dimension k of home C Cx square because in fact, this is a model for this multiplicity space. So they have the same dimension. So let me see. Because C Tx equals there, so the same idea. Mx prime tensor home Cx prime x. So when you dimension k of that equal sum for x prime in O dimension k of mx prime delta xx prime equal dimension k of mx. So we prove that the dimension of that dimension equal to that. So you can replace that by that, and so you get this equality. As I said, the second equality is okay. Is already explained, so that was an easy exercise. Okay, explaining this equality. Okay, so now, but in fact, this is exactly the cardinal of the set we mentioned. This sum of square. Because the set you have I will rewrite the set. You will see the indices. It's vary on x and ij. So that's why you have a square. But sum of ix square x in O is precisely the cardinal of the set tau x ij x in. So I say set, I write it as a sequence. You see, so you sum over that. So okay, you have this sum, and you have 2. This is 2 times. That's why you have the square. Okay, so it's okay. But so this is precisely the cardinal, and of this set whose element, as we mentioned before, are linearly independent. In OMCTT. So they form, the set form. So they form, so it form what? They form. This element form a basis of OMCTT. So we got our basis. Now we can decompose any morphism in this home space using this basis. Now, let gamma be a morphism in this home space. Then you can write gamma as a direct sum, as a linear sum of the element of the basis with some coefficient. Then for all x in this set, and for all ij in ix, there is a unique, but we don't need unicity, xij in the field, this coefficient, such that gamma equal the sum x in ot sum ij in x lambda xij tau xij. Any element decomposed. Okay, so what about now? So what there remain to prove? Yeah, we remain to prove what this is equal to. So this is equal to trace of gamma composed with tau xij times dimension of x. So next, for whole x prime in this set, KL in this set, if you compose gamma with tau x prime KL, it is equal to sum so x in tau ij in ix lambda xij of tau xij composed with tau x prime KL. But we know that this is, so we know the formula for that. It is you have 2 Kronecker delta, dimension x inverse. So the relation we proved just before. So it's equal to the sum for x in ot ij in ix of lambda xij delta x prime delta gk dimension x inverse tau xil. So the trace of all that, the trace of gamma composed tau x prime KL equal to the trace of that. But here, so here you can take x equal x prime. You can take g equal k, you can take I equal L. So it is exactly x prime KL dimension x inverse. And so this, so if, so you get this equal to that times that without the inverse. In general, for all x prime KL, so you can write it with xij if you prefer. Thus, xij equals the trace of that times the dimension of X. I just yeah, and the result follow. Not yet. So we have, it remains the identity here. So we prove that. Now, what about the identity? So how to simplify? So it's immediate. Finally, trace of identity of T composed with Ij equals the trace of tau Xij, and we know that this is Kronecker delta. So we can simplify the formula for the identity, and we are done with this proposition. Okay, so it remains 12 minutes. So we are done with this proposition. Resolution of identity. You see, it took 1 slide, 2 slides, 3, 4, 5 slides for it. Okay, so we are done with section 3 about preliminary or diffusion category. Now we are ready to prove Wang's conjecture. So let me mention that, in fact, an anecdote. We submitted this paper in a very good journal. I remember something like Duke. And unfortunately, it was rejected from Duke. So we resubmitted in another very good journal, but a little bit below Duke. And in the one reason why it was rejected, the referee was saying, okay, they are proving a new conjecture. They are proving one conjecture which was unknown, but the proof is very short. And I was very angry because the proof of that require all the preliminaries we did before. So of course, sure, because we will apply mainly all the lemma and proposition we proved before. But if you put all the preliminary in this section, that will be much longer. But so sometimes the referee reports are so annoying. So anyway. So I will state. So remember, recall that if Y is a simple object and Y star equal Y, so subcell dual, then home C of Y, this is one-dimensional. This is one-dimensional because it's self-dual. So right, this one, because it's dimension, because it is isomorphic to. This is isomorphic to home C of YY, which is Y is simple. So this is one-dimensional by Schur-Lemma. So this is isomorphic to that by what we call the high-junction isomorphism. So you can move this home space in more general. You have some home space X, Y, Z, and you can move Z on the other side here with a star, left or right, so that this moving is provide isomorphic home space, so of same dimension. So this has a dimension of from Y and Y, but Y is simple. So by Schur-Lemma, it's dimension Y. Okay, and so then this is one-dimensional, so you can apply our proposition 215 about Frobenius-Shaw indicator. It said that if you have something like that, then the Frobenius-Shaw indicator is a root of unity. Here, a second root of unity. So by our proposition 215, the Frobenius-Shaw indicator of y square is equal to 1. Okay, so in this case, so here the category is a pivotal monoidal, fusion category. In this case, the second Frobenius-Shaw indicator of y is minus or plus 1. And the next theorem will give a condition for this to be 1, not minus 1. Okay. So let me recall that this is Frobenius-Shaw indicator. Frobenius-Shaw indicator. Okay. So this section is dedicated to prove following theorem about Frobenius-Shaw indicator. Theorem. So this theorem is written in the paper in the introduction. I did not state it in the introduction of the course. So that's why it's 1.1, because it's stated in the introduction of the paper. So let C be a pivotal fusion category. Let me write here in the pivotal fusion category, even if fusion may not be required here, maybe just monoidal K-linear, semi-simple, I don't know, semi-simple, algebraically closed field, etc. should be enough, but anyway, does not matter. It's okay with a pivotal fusion category with algebraic closed field. So let's see be a pivotal fusion category. Let X, Y be object of in C okay, such that y is simple. So you don't assume x to be simple. You don't need to assume x to be simple here. Y is self-dual, and the home space of x tensor x dual tensor x with y is odd dimensional. This is the key assumption. Otherwise, it's not true. In fact, we will mention a counterexample for that. Then the Frobenius indicator of y is equal to 1. So it cannot be minus 1. Okay. And the proof is by contradiction. I will explain next week. If it is minus 1, then somewhere in the proof you will have you will consider minus 1 power this dimension, which is odd. So you will get minus 1, and this will provide a contradiction. If it is even, the minus 1 power even is 1, and so you cannot get the contradiction. And that we will mention a counterexample for the even case. So you have an easy assumption forcing this simple object to be of second Frobenius indicator 1. It cannot be minus 1 in this case. So let me finish mentioned mark. X is not assumed simple. There's no need. And let me remark that it may be useful for non-commutative Grothendieck ring. So the point is that you are our point here is to make some categorification of fusion ring. And at some point, we will need the Frobenius indicator. So you look the fusion ring, and you look for two basic objects of the fusion ring. So one basic object, one object of the, not basic, not necessarily basic, in fact, one object of that dual have a component with odd multiplicity. This is that you have the fusion ring, and we want an object so like this as odd multiplicity, and that we get automatically that as the potential categorification as this Frobenius indicator. And you look first for X basic element, but you can also look X non-basic. Can be some direct sum of basic element, and that makes sense to consider direct sum of basic element only in the non-commutative case. In the commutative case, considering a direct sum of basic element reduced to considering basic element. But in the non-commutative case, it may not. That is why it is useful to do not assume X to be simple. Okay, so that will be proved next week. So let me mention orally that, so end of session. But for the even case, there is a counterexample with a group representation fusion category with a group of order 72. So we found the group is PSU32, and you have this counterexample. We found, and also it was found independently by Yilong Wang in the unpublished note. So 72 is the smallest possible order for a group such that representation group fail, the category of representation group fail for this theorem in the even case. Okay, so see you next week.